representing a large scale system with few significant factors, significantly reduces computational requirements. Common method for dimensional reduction are linear algebra based method. Here in this principal component analysis PCA, singular value decomposition SVD, and second method is neural network based methods. In this you can see autoencoders, variation autoencoders, and benefit from this dimensional reduction are simplifies the representation of complex large scale systems, efficiently manage computing resources. Now let's talk about the 2D matrix. 2D matrix capture morphological similarity and relative scale among variables. Consideration of multivariables jointly enhances robustness, effective in detecting anomalies during specific time points. Two representative 2D matrix definition are matrix with inner products. You can see in equation 11, calculates inner products of variables at different time points, detects anomalies when the entire variable phase suddenly changes, and in the second equation you can see in equation 12 is matrix with differences. Compare differences between the variables at different time points, detect anomalies when the overall phase changes or drifts. Now let's talk about the graph. Graphs offer an explicit topological structure, enable learning of causal relationship among variables. Recent advances incorporate attention mechanism in graph neural network GNNs for improved performance. Here you can see the attention mechanism in GNN. Here you can see the formula. Attention layer computes the efficient for each node. Here sigma is the sigmoid activation layer function. Alpha represents the attention score, measuring the influence of node J on node I. Advances of graph-based neural reduction are explicit repetition of causal relationship, improve ability to identify root causes of anomalies, enhance anomaly detection accuracy. Now let's talk about modeling temporal context. Here are four types of neural network you can see. First one is recurrent neural network, second is CNN, convolutional neural network, third is hybrid approaches, fourth is attention mechanisms. So now let's talk about anomaly criteria in deep learning models. Deep learning models are trained to detect anomalies based on defined objective functions. Anomaly criteria are expressed as a numerical anomaly scores. Understanding the criteria for definition anomalies is crucial. Scheme for driving an anomaly score can be classified into three types. First one is reconstruction error, second one is prediction error, third one is dissimilarity. Now here here it is given an experimental setup. You can see here to compare the performance of the presented methods, public time series data sets are used. The first data set is secure water treatment SWAT, second one is water distribution WADI, third is Mars Science Laboratory Robot MSL. These data sets vary in terms of duration, structure, and presence of anomalies. Evaluation metrics can be used as precision, recall, and F1 score. Precision can be defined as true positive divided by true positive plus false positive. Recall can be defined as true positive divided by true positive plus false negatives. F1 score can be calculated as 2 into precision into recall divided by precision plus recall. Hyperparameters are vary depending on method used. Common hyperparameters include downsampling ratio, window size, pointer adjustment, and learning rate. Downsampling is used to speed up learning and reduce data size. So now let's talk about the result analysis of the experiment we have done. So comparison of state-of-the-art methods on benchmark datasets, SWAT, WADI, and MSL. Methods categorized into AE, VAE, GAN, RNN, Transform, and GNN. Performance metrics are compared to identify the strengths and weakness of for each method. Considerations include modeling temporal dependencies, parallel processing for long sequences, dataset dimension, and interconnection between attributes. No one size fits all method. Performance varies by dataset and goal. Models that capture temporal dependencies outperform those that do not. Parallel processing is advantageous for handling long sequences. So some detection strategies are real-time versus early warning, and the second is sliding window versus incremental update. So here you can see that real-time versus early warning. The first start with real-time detection. It is suitable for online business, finance, and manufacturing. Provides quick response to incidents, reduce costs caused by false positives. Examples are like GRU based and CNN based models. Inference time depends on computational complexity and resources. And here next one is early warning detection. essential for preventive maintenance (PDM) in manufacturing, predicts future breakdowns and minimizes downtime. Challenges include false alarms and missed anomalies, requires optimal threshold selection for anomaly detection. Examples are like LSTM based and STM based models. Now let's talk about sliding window versus incremental update. Sliding window. First talk about sliding window. Suitable for models with fixed input sizes, window size affects the length of temporal dependency. Careful selection of window size based on dataset characteristics. Examples are like TCN based and CNN based methods. Second one is incremental update. Beneficial for streaming environments with one by one data supply. Reduces computational overhead compared to sliding windows. Examples are like auto-regressive models like GPU and LSTM. Some methods support incremental updates while others require reference to the past data. Now let's see some training and preprocessing techniques. Here three preprocessing techniques we'll discuss. First one is loss function, second one is batch learning versus online update, third one is denoising. So first let's talk about loss function. Here you can see many types of losses. First one adversarial loss. You can see the formula. By this formula we can calculate this loss. Second one is reconstruction loss. There is also another formula. We can calculate this by. And the third one is prediction loss, and fourth is negative log likelihood. And here is the formula for negative log likelihood. We can calculate the loss function by using this formula. Now let's talk about batch learning versus online update. So first let's talk about batch learning. Deep learning assumes a extension data distribution. Models trained on a batch of data sample from same distribution as test data. Many may pose challenges where recollecting data is not feasible after each update. Let's talk about online update. It supports fine-tuning with newly appended data without retraining from scratch. It's rarely found in deep learning models due to conventional assumption of stationary data. Some deep learning methods address thresholds for decision making. Now let's talk about denoising. It is a technique for noise reduction. And you can here it's given some technique for noise reduction. First is smoothing, second is transformation, third is estimation, fourth is deep learning. By this I am concluding my slide. So let's see some ending points. So we discuss the characteristic of time series data and the analysis of reactive theorem. We provide a review of the latest deep learning based model and detection method for time series data from several perspectives and report the evaluation results on 3 real world benchmark datasets. We also discuss various applications of anomaly detection in several industries, including manufacturing, energy management, cloud manufacturing, and structured health monitoring. Finally, we finish with guidelines for model selection and training techniques. So, thank you. I hope you enjoy my presentation.